Hi, welcome to another episode of Proof Pilot. We are here to talk about second countable spaces, but before that, I want you to hit the subscribe button and like the video if you enjoyed it. And if there is any question about the subject, I will gladly answer to them in the comment section. I would really love if you give me some feedback. So we've encountered the first countable spaces. Now here is the second countable spaces. And this is the definition. A topological space is said to be second countable if it admits a countable basis for its topology. Uh, just a quick reminder of what a basis was. A basis had two conditions, that every element of it is an open subset of your topological space, and every open subset is the union of some elements of your basis. This was just a reminder of what a basis is, and the obvious example of a second countable space is the Euclidean space. Okay, so this is an obvious example. This is a second countable space. And why is that? I will show you in a second. So let's just take the Euclidean space as a line, and you can choose all the rational points in this line. Okay, so let's suppose that this is all the rational numbers in this line. And then you just take neighborhood of each of these points. Okay, so just draw an open ball. And as you can see, these points are rational. So the number of these open balls are rational, are infinite, but countable because the size of them is the same as the size of rational numbers, and since the radius is also a rational number, this actually becomes something in the size something at the same size of the size of rational numbers, the power of 2, and this is of course countable. And this thing right here is a basis for your Euclidean space. There is another definition which we are going to use this definition to discuss an important property of second countable spaces. So we are going to talk about the cover of X. What's a cover and what's an open cover? And there is something called a subcover. So let's suppose that you have a space X, okay, and cover of your space would be the set would be a collection of sets which literally cover your space. Okay, all of if I take all of these open balls and put them in a set, then this collection of sets will be an open cover, will be a cover of X. If all of these balls are open subsets of X, then we call this an open cover of X. And if all of these subsets are closed, then we call this a closed subset, a closed cover of X. So what's a subcover? Let's suppose that we have a cover right here. If I could somehow pick some of these balls and then I could again cover the whole space, then I would say that this is a subcover of my original cover. As you can see, this thing right here still covers X. Okay, so we call this a subcover. Now, the interesting property about the second countable spaces are brought here. As you can see, an instant observation is that if X is a second countable space, then X will be a first countable space. Why is that true? Well, let's just remind you that what a first countable space was. A first countable space was a space that at each point we have a neighborhood basis. What was a neighborhood basis? It was if you take an if you take a neighborhood of a point, then there is a set from your basis which contains your point and is a subset of that neighborhood. Okay, that was the definition of a first countable space. And as you can see, a second countable space is much more stronger because it's saying that it's a countable basis. Okay, these spaces have countable basis. It means that you can create each neighborhood with a countable set of open sets. So the first countable is easily satisfied. Now we reach to the second property. It says that X contains a countable dense subset. If you forgot what a dense subset is, here's a reminder. A subset A is dense in X if the closure of it equals to the whole space. Okay. To prove this, just let's remind you what was this meant to us. It was the union of all limit points and the whole space itself. So I want to prove that if X is a second countable space, then it contains a dense subset. So if X is a second countable space, then it has a countable basis. Okay, so X has a countable basis. And I want to call this basis as B with this notation. And this is, in this set, we have these subsets, these open subsets. So if I take each of these open subsets and just take a point from each of these subsets, and I'm going to call them xi. So each xi is a member of ui. Then I can see that those points that are not in any there are not in any of my basis elements, then they will be a limit point of some xi. So for some I, those who are not in my selection, then they will be a limit point of that element of my collection. The third one is a bit more complicated, and we get right into it. It says that every open cover of X has a countable subcover. Let's prove this part right here, that every open cover of X has a countable subcover. So as we know that our space is second countable, so there is a countable basis. Okay, so let this B be the countable basis. Now, I want to show that there exists a subcover, which I will show it with u prime, and this u prime is in fact countable. So let's just take some elements from our countable basis. And how am I going to take those elements? I take those elements if they are contained in some set from my cover. Okay. If they are contained in some cover, then if they are contained in some open sets that is a member of my cover, then I will take them and put them in my new basis, okay, which I will call it B prime. Now, I want to take those open subsets from my original cover and show them with this UB, which B is a member of B prime. Okay, so I claim that this is in fact U prime. The countable part is obvious because this thing right here is countable, and that's because just it's a subset of the original countable basis. So a subset of a countable set is countable, and it just remains to show that this thing right here covers the whole space. So let's just assume that X is a member of X. And if X is a member of X, then X will absolutely belong to some open set, okay? And an open set, we know that each basis will be contained in open set, and X in fact would be in this element of our basis. So as you can see, this thing right here actually covers the whole space, and that is the whole proof of this section. I hope you have enjoyed this video. See you in the next ones.